Good morning. Thanks for coming to my talk, and thanks to NANOG for this opportunity. So I'm Srikanth. I'm a graduating PhD student across the street at Georgia Tech, where I work with Professor Feemster. So today I'm going to talk about our recent work on how you can measure web performance bottlenecks in broadband access networks, and also how you can mitigate them. Okay, so web performance counts. So to the extent that many content providers spend a considerable amount of time and effort in trying to reduce page load times. And recent studies have shown that users are very sensitive to even a few hundred milliseconds. For instance, a study in 2009 showed that a 500 millisecond delay causes about a 1.2% decrease in Bing's revenue. Similarly, about a 400 millisecond delay causes about 0.75% decrease in Google's searches, and just a 100 millisecond delay causes a 1% decrease in Amazon's revenue. So when it comes to web performance, it's no great exaggeration to say that every millisecond counts. And as you might expect, there's been a lot of effort gone into this, trying to improve response time over the last decade or so. On the client side and the home network, you have really intelligent browsers now that do all sorts of caching, DNS, prefetching, content caching, and you have new protocols like Speedy and Quick. Content keeps moving closer and closer to the user with CDNs. You also have DNS servers that are right at the ISP's edge. Now on the server side, you have TCP optimizations like persistent and parallel TCP connections, bigger initial congestion windows for TCP, and also all sorts of content optimization. However, with more and more people accessing the web from homes, the question we ask is, what about the last mile? What are the effects that the last mile has on web performance? It must be obvious that throughput is an important factor. However, we found in a study a couple of years ago that the last mile latency can be pretty significant for many broadband users. For instance, we found that more than about 50% of AT&T's DSL users have a last mile latency exceeding 20 milliseconds. So obviously, any sort of optimization that you might implement are affected by last mile performance, latency as well as throughput. And this particular effect has not been particularly studied. So in this talk, I'm going to do two things. So I'm going to first present the results of our study that measures the effect of the last mile. And then we also look into some basic techniques on how to mitigate them. So first, for the measurement part, we use data from the FCC SAMNOS study. They have home gateways deployed in more than 5,000 homes across the US. And we basically find that page load times stop improving as the access link throughput exceeds about 16 megabits per second. So how do we measure the effect of the last mile on web performance? Now, there are many challenges to this. First is, how do you instrument end host? If you want to measure from the end host, how do you instrument it? And a fundamental issue here is that there's no real concept of ground truth. Which browser do you measure from? Which browser do you instrument? And different browsers implement different optimizations, and sometimes they implement the same optimization in different ways. And there are also other confounding factors that could affect performance: your choice of operating system, your choice of end host, many different things. So in order to get around that, we like I said, we exploit the FCC SAMNOS deployment and measure directly from the router. So this gives us the advantage that we have a broadly similar set of hardware that we can measure from, so that's one confounding factor out of the way. And we also have longitudinal measurements over multiple weeks, and that gives us a much better characterization. So for this, we use a tool that's been developed for this platform that's called Mirage. and it essentially emulates a basic browser function. It estimates page load time. I'll show you how. And it also, more importantly, breaks down the fetch latencies for every object when it downloads the web page. So, like I said, it's been deployed by SAMNOS in the FCC deployment, and it profiles 9 popular sites. Both the measurement and the code are publicly available from the FCC's and the SAMNOS sites. So, for those who don't know about the SAMNOS deployment, here's a little bit more detail. Back when we did the study, about 18 months ago, we got the data from about 18 months ago. The deployment was about 7,000 strong, and we used data from about 5,500 homes. It's a Netgear 3500 router that they deploy across many ISPs. We use data from about 11 ISPs with the most number of users. And we profile 9 popular websites. This is the list, and we use data from September 2012 for the study. Okay, so a quick primer on how Mirage and any regular web browser works. So you feed it a URL, and it looks up the URL and gets the IP address. That takes some time. And then it connects to the server, completes a TCP handshake, and then it sends a request for the landing page. And there's a server processing time as the backend server processes the request, and then it actually fetches this object. It then processes this object, and then gets a list of the objects that it needs to fetch to render the whole page. And then it uses parallel and persistent TCP connections in order to fetch the rest of the page. So Mirage is different from regular browsers in a few important ways. As you can see, it has a few grayed out lines, and that's because it's a very lightweight tool, and it does not resolve or fetch active objects. So it doesn't really attempt to establish ground truth. However, what it does is give us a pretty decent estimate of the page load time. And as you can see, it also breaks down every fetch into its constituent parts. So we actually get the individual latency times. Sorry. So here's the first result. So this is a box plot that shows across all the users the time it takes to load each of these web pages. So the box plot shows the interquartile range. And we also see the average page load time, which is denoted by the X, and the median, which is denoted by the red line somewhere inside the box. So what this shows here is that the median page load time exceeds 1 second for even the popular sites, for most of them actually. And as I showed you earlier, this is pretty high because users are very sensitive to high page load times. And in this one case with Yahoo, the median page load time actually exceeds 2 seconds. So you might expect, okay, it could just be users with low throughput. And that is true to an extent. And to study that, we break down the users according to their last mile downstream throughput. So, and this graph shows the result of that. So on the x-axis, we have bins of downstream throughput, 0 to 1 Mbps, 1 to 2, 2 to 4, etc. And on the y-axis, you have the median page load time for these websites, and this is log scale. So what we see here is, as you might expect, as throughput increases initially, the page load time decreases pretty drastically. However, it plateaus and doesn't really improve beyond a throughput of about 16 megabits per second. And the reason for that is pretty obvious. As you can see, for many of these fetches, the time is actually, for many of these objects, the time is actually dominated by latency. You have the lookup time, you have the connect time, you have the processing time, and none of this actually depends on your throughput. It's only the object fetch time that depends on the throughput, and even in this, the objects are so small. With modern websites, you have objects that are kilobytes, even sometimes less than that. So TCP's overhead in ramping up, and with latency, end-to-end latency, the TCP overhead is so high that we saw in some cases that the latency to just connect and wait for the object can far exceed the time it takes to actually download the objects. So latency overhead is very dominant, especially for small objects. So, and in order to see the effect of the last mile, we broke down the users according to the last mile latency, which is the latency between the home and the edge of the ISP's network. And this graph shows the page load times for this. So what you see here on the y-axis is last mile latency is broken down in 10 millisecond intervals. And on the y-axis, you have the page load time, again, in log scale. As you can see, as the last mile latency increases, the page load time keeps increasing. And as the latency goes beyond about 20 or 30 milliseconds, you have actually a very drastic increase in the page load time. And this is log scale, so this actually translates to a pretty significant increase in page load times. And as I told you earlier, we actually saw that many DSL users, in particular in the US, have last mile latencies that exceed 20, 30 milliseconds, and so their web performance could suffer pretty drastically. So now that we know exactly what causes slow web page load times, we look into how we can mitigate them. We look at a very simple technique called popularity-based prefetching inside the home and see how effective it is. So as we saw, a lot of the optimizations that exist don't really take into consideration the last mile latency. CDNs can only come up to the edge of the ISP's network. They cannot actually compensate for the last mile. And many client-side optimizations in the browser, they're application-specific. So even if you use 2 instances of the same browser, you cannot exploit any common browsing behavior, let alone across users inside the home. So the solution to that is pretty simple. We do prefetching inside the home, but we do it on the home gateway. So the idea is that you can maintain a popular domains list in the browser based on usage of the users, and then as people browse, this list gets updated, and the gateway can periodically refresh DNS records and maintain OpenTCP connections to the popular websites. And this can be done. We have a prototype implementation that can run on your home gateway. So we look at how this actually works. You might ask, you might say that a lot of these optimizations are already implemented in the browser. So we first evaluate the improvement that you can hope to get by this technique by looking at performance improvement in the best case. And we test this on the Bismarck platform using Mirage. We also, in the paper, we also look into how this complements existing browser optimizations by using Phantom.js. And then we also look into how we can actually make this practical. So I'm going to talk about how we evaluate the performance of this in Bismarck and also how we can make this practical. I encourage you to look at the paper to look at the other results. So a quick note on the Bismarck deployment. So Bismarck is a project that's led by Georgia Tech. The goal is to enable experiments and measurements from home networks, kind of like Planet Lab, but for the home. And for this study, we use 64 homes across about 15 countries, but currently the deployment is about 175 active home gateways across more than 25 countries. And all our data and all our code is online, and you can get more information from our website, projectbismarck.net. So to look at the effect of DNS prefetching, we ran this experiment using Mirage. So first, we clear all the caches in the home gateway, and then we fetch the page using Mirage, and we then fetch the page again. Since Mirage is just a command line tool and it doesn't cache content or maintain OpenTCP connections across multiple runs, so the difference in the the load time that we get across these two fetches just gives us the benefit of DNS caching. And what we found was this prefetching could improve page load time, according to website, by up to 10%. And now, to look at the effect of TCP connection prefetching, we ran a similar experiment, but we used an HTTP proxy. I'll tell you why. So we first clear the cache, and then we fetch the page through the HTTP proxy. I use Polypo in this case. And then we just clear the content cache in the HTTP proxy, and then we fetch the page again. So since the HTTP proxy will maintain open TCP connections, this gives us the benefit of reusing these connections across multiple runs. And so we found that just using TCP connection caching could improve page load time by up to 35%. And remember, this is without content caching. So this is a pretty significant improvement. So, well, maintaining open TCP connections to a lot of servers is not entirely practical. So in order to do that, we thought about how we can reduce the overhead of this prefetching. So the solution is, of course, popularity based, and we prefetch only the DNS request and TCP connections for only the popular sites. And we also implement a timeout. And we analyze the effectiveness of this using browsing traces from users from about 12 homes. And we run a simulation based on those traces, and we test different list sizes and timeout intervals. And we found that a cache size of just 20 popular sites with a timeout of 2 minutes could offer pretty significant improvement in cache hit rates. So essentially what that means is you only need to prefetch for 20 popular websites, and you also need to only have a timeout of about 2 minutes. So if the user doesn't go back, so if no one goes back to the site for 2 minutes, you just stop prefetching. And this essentially tries to exploit browsing behavior across multiple users. Many people go to common websites. So, and we found that cache hit rates improve quite significantly, and that translates to pretty significant improvement in page load times. So, in conclusion, so we saw how page load times could be very high, even for popular sites that you might expect would be highly optimized, and that latency is a major bottleneck, especially as downstream throughput exceeds about 16 megabits per second. And we also saw how a simple popularity-based prefetching technique could improve performance by up to 35%, and it's complementary to existing optimizations. The full paper, the data, and also the code that we used for this work is publicly available. I encourage you to visit our website, projectbismarck.net, and I'm happy to take questions now. And please also contact me over email if that works. Thank you.
We have time for questions. Over here.
Hi, I'm Wayne from Limelight Networks. One thing that I was wondering about while you were making your presentation was it's almost impossible for somebody to have a home network that does not involve some sort of forced proxy. And I'm wondering if you have any sense of whether that contributes to or helps to alleviate the sort of problem that you're discussing.
Sorry, what sort of proxy?
A forced proxy, where you basically can't access anything except without your connection being redirected through your vendor's proxy.
Well, actually, we haven't looked into that, but this should, at least that's what I think, it should work independently of that. I mean, it shouldn't matter to the ISP whether your request comes from an end host or from another proxy.
Well, my thinking though is that rather than making a direct connection to the site, you're going through another server, which adds additional processing time, additional latency, but it can perhaps compensate by having some data cache.
Well, we actually tested that. So we actually looked at the case where we did run a cache in a server that was pretty close by, less than about 20 milliseconds away. And we saw that this technique offers pretty significant improvements over that. So having a proxy in the ISP's network, it does help, but not as much as you would hope.
Jeff Houston, APNIC. In a presentation later on in this meeting, I'm talking about our observed performance of V6 versus V4. And I actually look very hard at the SYN handshake. And the question to you is, in what you've seen, do you see consistent evidence of trapping of SYNs on port 80? Because what we appear to be seeing is that V4 is slightly slower than 6 on port 80. And one of the possible explanations is there's a lot of infrastructure around to look for web fetches on port 80 in 4, but a lot less in 6, because people don't think 6 is real. Do you see any evidence in your study to back up that rather vague theory?
No, I haven't looked. Well, I'm not sure I understand your question. I'll be happy to follow up with you after this too.
Well, when I send a packet from home to some IP address port 80, is there a possibility that that packet won't get there because some intervening middleware will go, wow, I'm going to trap this connection and see what they're asking for because I might be able to answer it myself, as distinct from, say, sending the same SYN along port 443, I'm doing TLS, in which case it won't get trapped.
Okay, now I understand. So we haven't actually looked, but I think that's a good thing to look for.
Lee Howard, Time Warner Cable. I was going to ask a very similar question to Jeff. We're on the same panel later. I would love to see the first half where you're talking about your measurements. I would love to see a comparison of IPv4 and IPv6 fetching websites over both families to see which section is the same or different. And then I was thinking about next steps for this work. So you've identified a possible optimization for the top N websites. That's fantastic for the top N websites. I'm sure that those content providers are highly motivated to provide free hardware to consumers around the world so that their websites can go faster. But it doesn't affect the rest of the world, right?
So I would say that this actually would improve performance for the not popular sites because they're less likely to be as close to the user as the popular sites. The point of showing this was that even for the popular sites, which you would expect would be highly optimized, you see pretty significant improvement. And for those that are farther away, you would see even greater improvement.
So for a site that's not on a CDN, then the
Yes,
performance
so if
would
you
be
can
even
imagine-
faster because you have a TCP session, because once you've
Yes.
created the initial TCP connection, the long-lived session means the rest of the
so,
algorithm.
so we actually looked at kind of a similar issue. So what we did was since we have the deployment across the world, we actually looked at performance improvement in the US versus in Asia, for instance, right? And we saw much more significant improvements in Asia. So the theory is, content is farther away. I think, at least in the US, for the popular sites, it's as close as it can get to the user without actually being in the home, right? But it's not the case in Asia, for instance. And we saw very significant improvements, much greater than what I showed here for those users. So I assume that you can extrapolate this for the non-popular sites if you imagine that they're farther away from the users, even in the US.
Thanks.
Thank you.
Thank you very much, Srikanth.